So let's assume that for some unknown function, we have both partial derivatives and that we know that the mixed partials are equal. Therefore, this function would be fully continuous on a closed interval. And the question is, how do we figure out what function that is, being provided those things, being provided both partial derivatives, so this is a function of two variables, and being given the fact that the mixed partials are equal. So here in this video, I'd like to come up with a very generic formula that will accomplish such. So the biggest difficulty that we tackle, the biggest obstacle for us when trying to approach a problem like this, say if we're solving an exact equation or what have you, is the constant of integration. So for instance, I know that f of xy is equal to the integral of, and not sure what's going on with my stylus here, but I know that f of xy, let me fix that integral sign there. I know that f of xy is equal to the integral of, okay, so I know that f of xy is equal to the integral of partial f with respect to x dx plus some constant of integration, which is a single variable function of y. So the biggest dilemma now is to figure out what is this single variable function of y, which is the constant of integration. Do recall that upon partial differentiation, all constants are made 0, and when taking a partial derivative, any term that is not relative to what you are differentiating with respect to is a constant. So now, with that being said, if I took the partial of both sides now with respect to y, let's say I'm differentiating with respect to y, this f of x, y, which I know is equal to, well, taking the partial of both of this with respect to y, so f of xy is equal to the integral of partial f with respect to x dx plus c of y. So taking the derivative of both of these sides with respect to y, I end up with partial f with respect to y, and that's equal to the integral of partial squared f partial y partial x plus, now see here, the partial with respect to y of c of y. Let me actually write this in red. I think would be a good color. So the partial derivative with respect to y of c of y, that's just going to be dc dy. C of y, it's just a single variable function. That's just the derivative of c with respect to y. So to add to all that, we're just adding dc dy. So hopefully you can see where this is going now. If we subtract now the mixed partial integral, then we end up with dc dy equals partial f with respect to y minus the integral of partial squared f partial y partial x dx. So now, multiplying out the dy and solving this like an exact equation, we get that dc equals partial f with respect to y minus the integral of partial squared f partial y partial x dx, all of this multiplied by dy. So if both sides are then integrated, the end result that you end up with is that c of y is equal to this really hairy integral of partial f with respect to y minus the integral of partial squared f partial y partial x dx. Do understand this is an integral within an integral, and all of this is being multiplied with respect to y. So the final answer for our function then, f of xy, assuming that we are provided assuming that we have both partial derivatives of the function and we know that the function is fully continuous on a closed bound, then f of xy would be equal to the integral of partial f with respect to x dx plus, and this whole thing is the constant of integration. So to add to that, partial f with respect to y minus this other integral within it, partial squared f partial y partial x dx dy. So this is the complete expression for a function f of xy, and this formula will yield the result of f of xy for any function should you have both partial derivatives and should the function be fully continuous on a closed bound.